In today's lecture, I'll touch upon non-ideal liquid vapor systems, the ones that do not obey Raoult's law, showing both positive and negative deviations, resulting in an interesting feature called azeotropism. Then we'll take partially miscible liquid systems. Three good examples are there: Phenol-Water System, Trimethylamine-Water System, Nicotine-Water System. And lastly, we look at immiscible liquid systems to explain one interesting distillation process called steam distillation. Non-ideal systems. As I told you, this is the system which doesn't obey Raoult's law. There are two types. There can be positive deviation from Raoult's law, where the vapor pressure will be higher than predicted from Raoult's law. And we can also have systems showing negative deviation from Raoult's law, where vapor pressure will be lower than predicted from Raoult's law. See the phase diagram, or rather a pressure composition diagram. You can immediately notice the difference. In the diagram, if you look at, the dotted line shows the expected variation in vapor pressure if the liquids were to behave ideally. But it is clear that the experimental values of vapor pressure show positive deviation. The curve is much above that is expected from Raoult's law. It is true for both the components. Now, here it needs an explanation. Why liquids show positive deviation? It depends on the interaction between the molecules. If the interaction between the molecules of the same type, that is A and A, if it is stronger than between A and B, it is likely that B may not find place in the liquid state. A tries to push it out. Similarly, B molecules will be liking B molecules, therefore, A molecules are shunted out. Molecules are unsociable that way. If you don't like me, I don't like you. And that's exactly what is observed in the case of systems which show positive deviation. Now, look at the total pressure. The total pressure, which is the sum of the partial vapor pressures of the two components, shows a maximum. And the example that we have here is the mixture of carbon disulfide and acetone, which shows a vapor pressure maximum. But the diagram in which we plot temperature versus composition is more useful. Here is the diagram. You can clearly see that the two liquids have boiling points that are much different. A is lower boiling, that means it has higher vapor pressure. B is high boiling, which has lower vapor pressure, and you see there is a minimum here, which is called the boiling point minimum. So, these systems are the ones which show boiling point minima. Let us try to explain the usefulness of this type of diagrams. You start with a liquid mixture with composition corresponding to A1 and heat it. When we reach the point A2 on the curve here, which can be considered as the boiling point curve of various mixtures, at this point A2, the liquid mixture starts boiling. The vapors that emerge out has the composition given by A2 prime, and if we condense this vapor, we get a liquid having a composition given by A3. If we heat it, it liberates vapors having a composition A3 prime, and successively if you do this, condense the vapor to get the liquid and again evaporate that liquid collected, ultimately we reach the composition corresponding to the point C, at which the liquid that we have shows a sharp boiling point. It forms a vapor having the same composition as the liquid that we started with. And this liquid is said to have azeotropic composition. What do you mean by azeotropic mixture? Azeotropic mixture is the one which boils without change in composition. An example of the system that we have here is offered by a mixture of ethanol and water. Water has a boiling point 100 and ethanol 78.5. You have a system, a mixture of ethanol and water, which gives us a boiling point minimum which has 95% ethanol. Let us start with non-ideal systems, the systems which show positive deviation from Raoult's law. A pressure versus composition diagram is here. You can see both the liquids show vapor pressures that are much more than their ideal vapor pressures as expected from Raoult's law, which are shown by the dotted line. Why both the liquids show higher vapor pressure in the mixture than their ideal pressures? The reason is not difficult to find. It has something to do with the molecular interactions, interaction between molecules of A and interaction between molecules of B and between A and B. If molecules of A like molecules of A much more than B, then there is a chance that B molecules try to escape, and it's vice versa. Similarly, A molecules are not liked by B, therefore they also tend to escape. Molecules are also unsociable in a sense. As a consequence, if you look at the total pressure, which is shown here, which is the sum of the partial vapor pressures of the two components, the curve shows a maximum. So these are the systems where the vapor pressure maximum can be seen. An example that we have here is a mixture of carbon disulfide and acetone. There are several examples of this type. But what really matters to us, a phase diagram which we get if we plot temperature versus composition. You can see the liquid with higher vapor pressure shows lower boiling point, and a liquid with lower vapor pressure shows higher boiling point. So we have A and B with the differing boiling points, and the boiling point curve of the mixture, which is shown here, shows a minimum. So these are the systems which show boiling point minima. The upper curve shows the composition of the vapor that is in phase equilibrium with the liquid. Let us try to use this diagram. Let us start with a liquid mixture having composition A prime and heat it. Heating is no problem because we have 2 degrees of freedom, and when we reach point A2 on the curve, it starts boiling, the vapors emerge, and the vapors have a composition given by point A2 prime. And if we condense this vapor, we get a liquid having a composition given by the point A3, which is different from that of the original composition, which has become richer in the liquid A in this case, which is having lower boiling point. And if you take this liquid and heat it, you get a vapor having composition A3 prime, and successively if you condense it and then vaporize it, condense it, vaporize it, we end up with the liquid having a composition corresponding to point C. It's interesting here. If you heat this liquid mixture, it will boil at a constant temperature without change in composition. All other compositions will lead to a difference in the composition of the vapor except this point. Therefore, this point C is interesting. It is called the azeotropic composition. What is meant by azeotropic composition? We will look at slightly later. An example of this type of system is offered by ethanol water. It gives us an azeotropic mixture having the composition 95% of ethanol, which is called the rectified spirit. There are systems which show negative deviation from Raoult's law, and a consequence is very clear here. You can see the vapor pressure is lower than expected from Raoult's law, and the total vapor pressure shows a minimum which is much less than the ideal vapor pressure expected for the liquid system. An example that we have here is mixture of trichloromethane and acetone. Let us look at the diagram in which we have plotted temperature versus composition. As in the earlier case, it shows a boiling point maximum, and similar point C, which is the azeotropic composition, where the liquid shows a constant boiling point, which is therefore called constant boiling mixture, and there is no change in the composition. The rest of the discussions are very similar. If you heat a liquid of composition A1, it starts boiling at A2 to give a vapor having a composition given by A2 prime. If you remove this vapor, the liquid composition starts drifting towards A3 and ultimately reaches the point C. And further separation of the two liquids is not possible. So, it is possible for us to separate the two liquids till we reach point C, the azeotropic composition. So, one of the usefulness of the diagrams is to find out conditions where the two liquids can be separated in what is called distillation. But here we end up always with an azeotropic mixture, whether the system shows a maximum in the boiling point or a minimum in the boiling point. So, that needs explanation. These mixtures, as I told you, are called azeotropic mixtures. Let us look at an example of a system which shows boiling point maximum, that means shows an azeotropic mixture. This is offered by nitric acid. Nitric acid forms an azeotropic mixture with water having 68% nitric acid. You can see there is a boiling point maximum. The temperature is 120.5 degrees, which is more than the boiling point of nitric acid and water. Let us now try to explain what is meant by azeotropic. As we have seen, a mixture of this composition boils without change in composition. Our attempt to separate the mixture by distillation fails. Entire phase diagram has this point where the distillation is not possible. All other mixtures can be distilled in order to improve the purity levels. We have an example here which is like nitric acid. A mixture of HCl water also gives an azeotropic mixture having 80% water with boiling point of 108.6 degrees centigrade. There are systems showing boiling point maximum. One is trichloromethane acetone mixture, the other is nitric acid water mixture. And as I told you, there are systems showing boiling point maximum. Ethanol water is one example that we have seen, another is offered by Dioxane-Water System. Why azeotropic mixtures boil at constant temperature? We can look for an answer in the phase rule. We use the equation F is equal to C minus P plus 2. In this case, it is a two component system, that is why C is equal to 2. Number of phases is 2, and hence the number of degrees of freedom available to us is 2. But during the experiment, we have kept pressure constant at 1 atmosphere. We lose 1 degree of freedom. So, we have only 1 degree of freedom available to us. But there is a restriction imposed on the system. What is that restriction? At point C, you can see here where the two curves meet, the vaporous curve and the liquidous curve meet. What does that mean? The composition of the vapor and the composition of the liquid are the same, and this restriction takes away the last degree of freedom that we have. That means the system becomes invariant. The mixture therefore has to boil at constant temperature without change in composition. Phase rule has answer to this problem. But then the question arises, how to remove azeotropism, because such a mixture cannot be subjected to distillation to separate the two components. We can try various methods. One of them is freezing the mixture so that one of the components present in the mixture may freeze and hence can be separated. We can resort to selective adsorption, put a good adsorbent which selectively takes away by adsorption one of the components. Especially we try for minor component that is present in the mixture, or by chemical reaction, add some reagent which can react with it so that it can be eliminated, or we resort to extraction of the minor component if you have a suitable solvent extraction procedure. But we have heard of absolute alcohol. In the labs you might have seen there are two bottles, on one which is written alcohol and on the other absolute alcohol. What is the difference? Difference is here. Alcohol and water form an azeotropic mixture containing 95.6% alcohol, which we generally call rectified spirit. Some water can be removed from this by chemical reaction with quicklime and magnesium ribbon, but about 1% water still remains in it. It's very difficult to remove water from alcohol because of the presence of azeotropism in the system. Then how do you prepare absolute alcohol, which is nothing but 100% alcohol? Let us try a method. We use azeotropism to kill azeotropism. To the azeotropic mixture containing 95.6% alcohol, you add a calculated amount of benzene and distill the mixture. What happens? Benzene has a tendency to form an azeotropic mixture with alcohol and water. That means a ternary azeotropic mixture is formed which distills off very easily. Entire water is taken out, and what is left? Alcohol and a small amount of benzene, which is deliberately added in excess in order to ensure that all the water is removed. On further heating, this binary azeotropic mixture starts boiling, and a binary azeotropic mixture of alcohol and benzene distills off, taking away all the benzene, leaving behind 100% alcohol. That is our absolute alcohol. One of the best examples where we can use azeotropism to remove azeotropism and prepare absolute alcohol. Let us move on to partially miscible liquids. We have several examples of partially miscible liquids. We have dealt with completely miscible liquids in our last episode, where we discussed solid vapor equilibria, the systems that obey Raoult's law. In this part, we will take up partially miscible liquids like Phenol-Water System. Let us look at Phenol-Water System. The phase diagram is here. A very simple, you have a dome shaped region in which the system breaks into two phases, and outside this there is complete miscibility. Phenol and water are partially miscible. Therefore, if we take water at any temperature, say T1, and add phenol slowly with stirring, phenol dissolves initially, but when the solubility limit is reached, here on the dome shaped curve here, the system splits into two phases, one with this composition, the other with this composition. As you continue to add additional phenol into it, the relative amounts of the two phases will change, and finally we reach a system in which there is large excess of phenol, and again the miscibility is attained. Therefore, on either side of the dome shaped area we have complete miscibility, but within that the system is always split into two phases. You can see here, if we increase the temperature, the compositions of the two phases that are in equilibrium start coming closer together. In other words, the length of the tie line joining the compositions of the two phases decreases, and ultimately the length becomes 0 that is a point which is called critical solution temperature at which the two become miscible. Above this temperature, they always form one phase. So, point C is important. It is called the critical solution temperature. Let us apply phase rule equation to this. The equation is F is equal to C minus P plus 2. In the one phase region where phenol and water are completely miscible, C is equal to 2, two component system, phase is 1. Therefore, we can find out the number of degrees of freedom, which is 3. As pressure is kept constant, we are left with 2 degrees of freedom. The system is bivariant. In the two phase region where there is partial miscibility, number of degrees of freedom works out to be 1. The system is univariant system, but at critical solution temperature, that is at point C, the two phases become identical. The composition of the two phases become identical. Hence, the number of degrees of freedom F becomes 0. The system becomes invariant system. Point C, as I told you, is called critical solution temperature, abbreviated as CST. Since it is the maximum in the curve, in this particular case, it is called upper CST. It is a characteristic of the system. It needs some explanation here. Where do we use this? The domestic disinfectant that we get, what we call generally phenyl, is a system like this. It is a dark liquid but clear. If you add water to it, it becomes milky. So, why it turns milky? We take into account the effect of chemicals or impurities on CST. CST may be made to increase or decrease with the addition of certain impurities deliberately. In this particular case, you add a substance which suppresses the CST of phenol-water system, so that when you add water, it goes into the two phase region from the one phase region when it was supplied to you. Let us see the changes that are taking place when we deal with such phase diagrams. You start with the phenol water mixture with this composition. As you heat it and say take it to temperature T1, with this original composition, the system is in two phases, one with the composition A and other phase that is in equilibrium is with composition B. And as you heat it, say to temperature T2, the composition now of the two phases is A prime and B prime, and the relative amounts of the two phases are given by the tie line, the two arms of the tie line, and you can see one of the arms start decreasing in length, and as you increase the temperature, ultimately we reach the point A double prime here, and you can see that the amount of one of the phases, in this particular case B double prime, decreases almost to 0, and further increase in temperature makes the two liquids completely miscible. So, we attain miscibility from a two phase system by heating, and the miscibility is attained by the disappearance of one of the phases. If you start with phenol rich phase, you will have systems giving rise to miscibility where the water rich phase disappears. If you start with a particular composition, in this case given by X prime, and heat it, you can clearly see that the two phases remain in equilibrium till we reach the point C, at which both the phases are present and miscibility is attained. Till the last point, the two phases will be present, which means miscibility is attained when the compositions of the two phases that are present in equilibrium become identical, and therefore, this point is very characteristic of the system, and as I told you, it is called upper critical solution temperature. There are other systems which show lower CST, like the one that we have here, a system given by water and trimethylamine, exactly like phenol-water system, but the CST, the critical solution temperature, is at the lowest point here. This is called lower CST. Why miscibility is attained at lower temperature, which is unusual? Generally, we know that the solubility goes on increasing as we raise the temperature, and ultimately miscibility is attained at a particular temperature. In this particular case, the miscibility is there at lower temperature. With the increase in temperature, the miscibility decreases. Probably in such systems, there are some molecular interactions which are operative at lower temperature, which become weaker as the temperature is raised. When you have systems like these two, upper and lower CST, and interesting system we have here is the nicotine-water system, which shows both lower CST as well as upper CST. The explanation is similar. We have complete miscibility outside this circle, and within this you have the system in which there are two phases in equilibrium. Let us now look at systems involving immiscible liquids. If we take two immiscible liquids, 1 and 2, depending on density, they form separate layers. Liquid 1, which is denser, is cut off from the vapor phase. Therefore, only the molecules of liquid 2, which is lighter, will have chance to escape to the vapor phase. This is very clear, and therefore, in such systems, if we bring about agitation very strongly, both the liquids will have chance to enter the vapor phase, so that the vapor will be in equilibrium with both the liquids. In total vapor pressure in such cases will be the sum of the partial vapor pressures, but in the pure state. That means P is equal to PA naught plus PB naught. It implies that such liquid mixtures will boil at a temperature which is lower than the boiling point of either of the liquids. So, each liquid behaves independently and therefore contributes to the vapor pressure as if it is a pure liquid. This is true irrespective of the relative amount of each of the liquids present in the mixture, provided their amounts are sufficient enough so that they exist in equilibrium with their vapor. Now, boiling point of the mixture. If we take water as one of the liquids, which is immiscible with the other liquid which we take, like nitrobenzene, iodobenzene, etc., even aniline for that matter, the liquid mixture will boil at a temperature below 100 degrees centigrade. Take for example, boiling point of pure water, as we know, is 100 degrees centigrade, and that of aniline is 184 degrees centigrade. The mixture boils below 100 degrees, say around 98 degrees centigrade. Exactly similar arguments holds good for any other liquid mixture, whether water is present or not. So, instead of boiling with water, it is advantageous to use steam, because it heats up the liquid mixture as well as it brings about agitation, which is a requirement for both the liquids to be in equilibrium with their vapors. This is the assembly that we use in the distillation process, so that the liquid mixture that is present is made to boil over by passing steam, where the steam passed at vigorously agitates the mixture, the vapor gets carried, water as well as that of the liquid that is immiscible with water, and collected in the distillate. The process is called steam distillation, obviously because we are using steam. Why steam distillation? Normal distillation of such compounds is taking place at high temperature, because these are high boiling liquids. They may be unstable at that temperature. Therefore, if we use steam distillation, they can be made to boil at much lower temperature, even below 100 degrees centigrade, in this case because water is being used. What is the application? Definitely, it is to separate and purify compounds of this type, which we have mentioned earlier, which are said to be steam volatile compounds. These are generally the natural products that are very sensitive to heat. Some of them are steam volatile, and steam distillation can be effectively used to extract such plant materials like eucalyptus, citrus oils, and natural oils which are used in perfumery from the plants. It is found that in steam distillation, the composition of the distillate is fixed irrespective of the relative amounts of the liquids present in the mixture. And to explain this, we can use phase rule equation. F is equal to C minus P plus 2, and if we substitute the value of C as 2, P as 3, we get F is equal to 1. But we already have kept pressure at constant at 1 atmosphere, which means that the system becomes invariant. The degrees of freedom F becomes 0. Therefore, the mixture of the two immiscible liquids will boil at constant temperature with fixed composition of the vapor. That means the distillate will have a fixed composition. We can calculate this by using the familiar equations that we have, and you are already familiar with it. We have come across these equations which relate the pressure, the partial pressure, the mole fraction in the vapor phase, the number of moles that are present in the system, and ultimately we can calculate and show that the ratio of the number of moles of each of the solutes or each of the components present in the distillate is constant. And in fact, we can calculate the weight ratio by substituting the values of molecular weight in the equation, and so that WA by WB is equal to PA0 into MA divided by PB0 into MA, where MA and MB stands for the molecular weight, a constant ratio as expected. This equation in fact has been used earlier to find out the molecular weight of compounds that are freshly isolated. Let us summarize what we have seen. We have seen today non-ideal systems which show positive and negative deviation from Raoult's law. We saw what are azeotropic mixtures. We looked at partially miscible liquid systems which show upper CST, lower CST, as well as upper and lower CST. The examples are here. Finally, we looked at immiscible liquid systems, which are interesting because we find a process very important in organic chemistry, that is steam distillation. So this brings us to the end of our discussions on phase equilibrium. What we looked at? We started with the definitions of terms involved in phase equilibrium. We derived the phase rule equation, then saw the application of phase rule to one component system like water, carbon dioxide, sulfur, etc. Then used our knowledge for applying it to two component systems where we saw solid liquid equilibria, liquid vapor equilibria, liquid gas equilibria involving miscible liquids, partially miscible liquids, and finally immiscible liquids.